Hi guys, and then I hope that you're enjoying the lecture so far. What I have to say is like networking is fun. It's very fun. I can tell you that. So we will be discussing about the one of the most interesting part in networking. So we'll be speaking about we'll be going in details into the the, the inner workings of a computer network. So to do so, we'll be going with a different approach. You might see a single video, but then they will be separated into parts. So we'll start the very first part with packet switching, and after that we'll go with the other sections bit by bit so that we don't lose focus. So let's start. When you send a message, right, or when you have a discussion like not a discussion. So when you basically send a message or you send a request over the internet, so you basically taking a piece of data and then you're trying to send it across the network so that the other the recipient of your file or your whatever gets delivered, right? So for your data to leave from one side to another, then we have to break that piece of data into packets. Imagine that you need to send 10 gigs of data from one side to the other. 10 gigs won't travel as 10 gigs. They will be broken down into smaller chunks that we call packets. So yeah, that's basically the name. They will be called packets. So in the network, we have these little entities like the basically components into the network we call switch. Like some of them are called packet switches. Yeah. So they basically save your packets and then they forward it to the next switch or to the destination. So each each packet transmitted at so you have the packets are forwarded from one router to another one. There is a protocol that goes in between, but then each packet is transmitted at full link capacity, and then we'll also see that in the later slides. So here you have a very simple example of how it works. So you have the source of the source, like which is a source computer, and then you have a destination computer, right? And in between you have a switch, a packet switch. So the procedure we'll be speaking about is store and forward. So see these little devices as computers, like little computers that can only do one thing, or let's say two things: receive a packet and pushes back the packet somewhere else. So to for that to happen, we rely on what we call links. So we have the transmission links, and each transmission link it's having a transmission rate, right? So they all have a transmission rate that each of them has a unit of bits per second. The other units can come later, like kilo, mega, giga. So it's depending on how you want to count it. So we have a delay between one point to another one, right? So that's for the transmission and the transmission delay. Now the store and forward part. These devices they have a limited amount, like they have a limited amount of memory. They cannot store a lot of things, right? But they can store packets of data that would leave from one side to another. And you can see that packet number one here leaves from the source to the switch, and then we leave this from the switch to the destination. So what it does, it stores packet number one into the switch, and it stores in what we call a queue, an inbound queue, and then we'll forward the packets and you will go to an outbound queue, and then you will go to the destination packet. Yeah, that's for the store and the forward part, right? And then the end delay, we have a 2 we have a 2L divided by R. Let me explain this one. So let's assume that we have, like we said, we have a transmission rate of R on each link, although in real life it's not always like that, right? And then we have a, like, the size of each and every packet, it's L bits, right? So basically the delay, right, the transmission delay between the source and the first, the transmission delay between the source and the first switch or the next network component, it's basically L divided by R, right? We have some results that will be in seconds, right? But then this is if we have one transmission between the source and this guy, which is a switch. If you want the full end-to-end delay, which is like, this is one what we call a one hop, right? And if we have another hop here, then you can see that it will be 2 times the previous delay that we had, right? So it will be 2x on this side. But then now if you have, instead of 2, and then in real life you have n of them, then it will be n times L divided by L, which is the size of a packet, right? The size of a packet in bits, and R, which is the transmission rate in bits per second. Remember, this is in bits, so it can be in megabits, it can be in gigs, it can be in kilobits, right? And that's basically that. Now, from the formula that has been just mentioned earlier, you can easily work out the transmission delay, which is in milliseconds. It's like it will be 0.0001 seconds. That has been just worked out for you. Cool. Now this is a very important part that you need to look at, and I'm sure you already experienced that before. Packet switching, queuing and delays, queuing delays and loss. So this happens a lot. Like, let's say we are at the University of Witwatersrand, and then everybody's there, there's no coronavirus happening, and we all want to get to Moodle, right? And that, let's assume that Moodle is, for example, computer C. Yes, it's computer C. That's for Moodle. We have a computer Z. So this one is Moodle. This one is, I don't know, it's that other thing for the students activities or whatever, and that's one, let's assume that this for residences. So remember from the previous slides we were speaking about the packets that were going to land into a switch, and they were basically, in a switch is in between 2 links, right? So if you have one switch, then you have 2 links, because it needs to link to network devices. So now we have to add a bit of complexity in there. Like in the previous slides, we assumed that all the transmission link were having the same transmission rates. But then in the real life, let's assume that from your computer A, and your friend's computer B, you have transmission link of each 100 megabits per second. 100 megabits per second. It means that your connection from your computer to the next computer component, the next network component is relatively fast, right? It's pretty fast. So what will happen? Is that here in the switch we have the inbound queue. So we'll be having a queue. So this is the inbound queue, and then we'll be having an outbound queue. And these are analogies that you know very well, right? Let's assume that you really want to look for Moodle, and then Moodle data is just like it's for everyone to see, right? But then two computers are now sending at a very high speed request. So I want to go to assignment 1. I want to go to assignment 2. I want to go to assignment 3. And each on every entries of this inbound queue has been sent by computer A and computer B. Computer A wants assignment 1 and 3. Computer B wants assignment 2 and 4. And then you see it just gets in by the order in which the staff has been requested. Now it has been sent at a transmission rate of 100 megabits per second, but then now it has been queued in the inbound queue. Everything is all right. Now on the switch here, between this switch, right, that received the request of our two students here, and then the next switch here that speaks to Moodle, so discard the other ones. So between this switch and the next switch that speaks to the computer that hosts Moodle, the transmission rate is 1.5 megabits per second. Imagine that you would want to keep on sending requests. This guy will be overloaded because it receives at a very fast rate request, but then it will send the request first in, first out. It's like it's a queue, right? So the request number one will go at a rate of 1.5 megabit per second. And since it is the case, this switch might be overloaded. So packet queuing and losses, if the arrival rate, right, to link exceeds the transmission rate of a link for a period of time, this is the arrival rate. The arrival rate is too fast. It's too big, right? So we might have some losses of let's say request number 5, because either this router will be acting very slowly, or it will be full in memory, right? That will be a problem. So packet will queue stuff and waiting for the transmission for the output link, for the outbound queue to be free, right? So that it can receive some of the things. And packets can be dropped, like I said, if the memory or if the queue is full. That's basically how it works. That's the reason why I say the network is slow, because there is a switch that has a memory or a buffer that is too full, and sometimes it will tell you that, okay, the page is basically out of reach because your request has been just dropped, and everybody is asking for Moodle information, and Moodle is there minding its own business, getting each and every request slowly, right? So that's basically how it works. All right. So packet switching, it's a very important concept that you need to know. It's like we have multiple stuff that happen into the picture. When a packet comes into a switch, right, there is a little protocol that it follows to leave from one end to the other end. So what it does, a packet gets into a switch, and then like each and every packet has some information. It's like like let's assume that you send a letter and then it goes to the post office. Then what we'll do, we have your name, you the sender, we have the name of the person that you're sending the letter to. Let's assume that it's Moodle or Google or whatever you would want to have response from. You have the address of the person that is basically receiving your letter, and your address is having some specifics: street name, suburb, area, postal code, country code, and stuff like that. Same for your packets. Your packet has some information, and one of them can be the 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 the, the sequencing order of the packet, the IP address of the sender, the IP address of the receiver, and multiple other things, right? So this is exactly what happens, right? So it's like, okay, your the IP address of the destination looks like the whatever you're trying to send will go to the US, and then you route it differently so that it goes somewhere else, right? So we'll take a very simple example here. Let's assume that okay, we won't do networking here, but then we'll do an example that you might understand quicker. Let's assume that you are in Johannesburg. I guess it's JHB, yeah, and then you want to go to Durban. To Durban is usually DBN. Now, what you do, usually flight from Johannesburg to Durban is just a one flight. It's a straight flight from Johannesburg to Durban. And you gave some information to the airline company. I would like to go to Durban. I'm starting from Johannesburg. And then they will basically do this type of protocol to say that this guy is living from Johannesburg to Durban. The problem is, like you see this example at the bottom here, and you know the airline traffic has many hubs. Like to go to Durban, you can the flight can literally do a lot of things. They say, okay, cool, then we can go to Cape Town first, CPT. So we will go to Cape Town, and after going to Cape Town, you will go to East London. After going to East London, then we'll go to Durban. We'll be going to Durban, but then you see that we've done multiple trips, right? It's like one hop and another hop, and we are having 3 links. This is very inefficient. But then when you say I want to go to Durban, then there's a straight route from Johannesburg to Durban, right? That's basically what these routing tables, that's what we call it, or forwarding tables are there for. So they basically tell the user how a packet needs to be directed from one source to the destination, right? So and another very quick example that's now related to us. Let's assume that you want to, this is an MP3 that you want to send to, I don't know, to your Google Drive. And Google is in the US. Or maybe yeah, let's say it's in the US. Now you have a couple of switches here. And this switch is related to this one. This switch is related to that one, and this one has some connection to this one and that one, and maybe this one is connected to this one, and we have one here. So the MP3, first of all, will be broken into packets. Packet number 1, packet number 2. You can take any route here. You like you see route 1, route 2, and then packet number 1, or let's say packet number 2, we come here, and you see that on Google Drive, we in the drive here, we have packet number 2. Packet number 2 arrived. Okay, let's call this packet number 2 and packet number 1. And packet number 1 came to this one, and then it stopped here. Okay, let's assume that this switch is connected to that one. Packet number 1 goes here, goes here, goes down here, goes up here, and packet number 1 finally arrives. Remember that each packet has a sequencing order. So what will happen? Packet number 1 will be put first, and packet number 2 will be put later on, and after consolidation we have our MP3, similar to our first MP3. The way the consolidation happens is outside the scope of this lecture. You will learn it later on. Alright, so the next step after this, we'll be speaking about packet switching, and this is where I'll stop the first part of our lecture. Take your time, let this thing sink in, and then go to the next one. Thank you.